Welcome back to the Mechanics of Solids lecture series. In this next series of videos, we'll be looking at examples pertaining to torsion in indeterminate shafts and thin-walled tubes. The objectives of this lesson, what I want you to be able to do at the end, is to be able to compute internal forces, deflections, or angle of twist, which is pertinent to torsional members, and shear stresses in 1 degree indeterminate shafts using considerations of equilibrium and compatibility. I also want you to be able to evaluate shear stresses in shafts with arbitrary shaped closed thin-walled sections on the basis of a simple approximation. Here's the first example that we'll look at. This is a problem from Mechanics of Materials by Timothy Philpott, Wiley 3rd edition. The problem statement reads, the torsional assembly shown in the figure consists of solid 2.5-inch diameter aluminum segments with a shear modulus of 4 ksi, those are the end segments 1 and 3, as well as a central solid segment with a 3-inch diameter bronze section with a shear modulus of 6,500 ksi. So I will go ahead and summarize that given information. The end sections have diameters D1 equal to D3 equal to 2.5 inches. We use the small d generally for solid sections. G1 equal to G3 equal to 4,000 ksi. And then section 2, the intermediate bronze section, has a diameter D2 of 3 inches, 3.00 inches, and a shear modulus G2 of 6,500 ksi. We are also given that concentrated torques of TB equal to T naught and TC equal to 2 T naught are applied at B and C, which we can interpret as TB equal to T naught 20 kip inches, and TC equal to twice that, or 40 kip inches. Okay? We're asked to find the maximum shear stress in segments 1 and 3, maximum shear stress in the bronze, segment 2, which I'll summarize as T1, T3, and T2 max. Know that T1 and T3 will be the same. Since our working units are kips and inches, we'll find those stresses in KSI. We're also asked to find the rotation angle at joint C, which I'll call theta C, and natural units would be radians. I will do a quick sketch of the segmented shaft over here. Here's our intermediate flange plates. Okay, we have segments 1, segments 2, and segments 3. It'd be a good idea for your free body diagram to draw the lengths in as well. I'm going to go ahead and omit them for this problem for expediency. Now I note that I have my torque T sub B at point B, or flange plate B. Let me label those. And I also have T sub C at flange plate C. And you can see that I drew those torques going to the right. And the way to determine that sign convention is to take your hand and wrap it around the tube in the direction of the torque. And you would draw the arrows for the torque in the direction that your thumb is pointing, which in this case, if I wrap my hand around the tube, my thumb is pointing to the right, or toward point D. So I draw the torques going toward point D. Okay, so now, based on this diagram, we can easily construct some equilibrium equations for the torque, for the internal torques relative to these applied torques. Remember that the approach that we use for equilibrium is to draw a free body diagram of each internal flange plate. That allows us to bypass the indirect reactions and solve directly for the internal torques. So here is our first flange plate at B. I like to draw my torques in the positive direction with the arrows, double arrows going out. So flange B is connected to segment 1 and segment 2, and also we have the applied torque T sub B at that joint. Taking my equilibrium equation, sum of the torques equal to 0, I would find T sub B plus T2 minus T1 equals 0. I'll leave it like that for now. Let's also do a diagram of flange plate C. And this has an applied torque T sub C. It's connected to segments 2 and 3, so internal torques of T3 and T2 with the double arrows pointing outward. From equilibrium on this flange plate, we would get that T sub C plus T3 minus T2 equals 0. These are my two equilibrium equations. Let me call those 1 and 2. Okay? Note now that if I look at the variables in those equations, the first equation has T2 and T1. The second one has T3 and T1. So I'm going to rearrange these and solve for T1 in terms of T2 and T3 in terms of T2. That means I would rearrange equation 1 to be T1 equals T sub B plus T2. And T3 is equal to T2 minus TC. That comes from the second equation. And these are the equilibrium equations I'm going to use working forward in the problem. Now my compatibility equation, since the shafts are connected end to end in series, we know that the total rotation of the system from end A to end D has to be equal to 0. So the sum of the internal rotations, theta 1 plus theta 2 plus theta 3, is equal to 0. We can solve for each of those equations using the relation between theta and the internal torque, which is T1 L1 over J1G, theta equals TL over JG, plus T2 L2 over J2 G2, plus T3 L3 over J3 G3 equals 0. And that is our third equation, our compatibility equation. So using this information, we'll go forward and solve the problem on the next video.